Okay, hello. I hope everyone's doing well. Are you excited today? We get to finish the last section of chapter 2 of learning vectors for physics. I hope you're excited. Sorry for the delay. I had tech issues as I always do. I tend to have tech issues when it comes to this sort of thing. The thing is, I set it up early and it still happens. Like, the tech issues still happen. But I guess it wasn't that bad this time. But yes, sorry for the delay. I hope you're ready to learn. Today, I am a bit tired, as I always say every day. But my brain is honestly quite smooth today. Everything, is kind of sliding right off. So we'll see how I do. I haven't actually had too much time to review this section of the textbook, so that means I will be just straight up relearning this again. I think we have how many more pages left? 1, 2, 3, 4, 5, 6, 7 pages, pretty much. 7 pages left, but hopefully that goes well. What else? Oh, I was gonna say something else. I'm preparing for spooky month slowly and steadily. I've got new games. I'm gonna play Observation Duty as my what's it called? My horror game of the year is Observation Duty. I hear it's short. It's not that bad. So there's that. I also got Strange Antiques, Love Ghosty, Night in the Woods, and I have Cult of the Lamb, and of course Baldur's Gate. So those are the games I expect to play during the spooky month. I probably won't finish them all, but if I don't finish them all in spooky month, I'll continue them on into fall. So I'll continue them on into November, and I will be having a bit of a hiatus in December. I don't have the perfect dates yet. I don't really know what specific dates, but I should be back on the last week of December for sure. I might be back earlier, but we'll see. But yeah, I'm excited for that. I'm on work sneaking the stream. Oh, no. If you have to work, go work. That being said, I'm a bit of a hypocrite because I've done that before. I've just lurked in other people's streams. I never usually type though. I feel like people can see and they're like, oh, what's that? Or some people know what VTuber is and they start judging, I tend to watch VTubers as well as like my mutual friends. I will lurk in their streams. But these days I feel like I can't do that anymore because people are like, why are you watching VTubers? Why don't you just watch a person? I'm like, I am watching a person. I'm watching a person be their most authentic self. Anyways, I'll stop talking. Let's get on to it. Okay. Observation Duty is the one where you work at night at the autopsy clinic. Yes, I believe that's the one. And then you just have to keep watching them and make sure everything is okay. I'm definitely gonna scream. That day I need to mentally prepare and just and breathe. But yes, that is the one where you watch an autopsy clinic. But for now, let's focus on the scary part let's focus on what some people find scary is physics. And I want to show that maybe it's not as scary as you think, and maybe you can do this. All right, cross products. So previously we learned about vector operations like add, subtract, as well as the dot product, which gives you the scalar product. So the scalar means it only has one value. It doesn't have magnitude and direction. It just has the magnitude. So you can get a scalar dot product. And for that, it's just this cosine. Can you see my mouse? You can't see my mouse. Hold on. Let me fix that for a second. Capture cursor. No, you can't see my mouse. Oh, there it is. Okay, so you can see the cosine. You can see the scalar of the two vectors. Find that scalar equation of the two with this AB cosine phi. and phi is the angle, and that's pretty much the most important part of it. They are commutative, which means they're able to be flipped around, and distributive, which means that they can be distributed just like a number in front of a variable, kind of like 2 times 2 plus 5, and then you can multiply that 2 into the 2 values in there. There's also this value, so you can get the cosine and then find the angle in between the 2 vectors. So there's a bunch of that. There's a lot of practice problems, and once again, this book is open source, so if you like to learn on your own, this book is completely free. It's open source. I think this OpenStax is a great resource for people who want to learn certain things. I think, yeah, they have a Python textbook that I plan on using next year in January for my Learn Python with Me series, because I think that'd be really fun. And that one's even interactive, so that's good. But for now, we're learning the vector product. So we're not just going to the scalar, we're getting the vector product of 2 vectors, which means the resultant has two values in a way, or has 2 pieces of information. So we have the cross product, and it says a vector product is a cross product. The vector product of two vectors, A and B, is denoted as A cross B and is referred to as cross product. The vector product is a vector that has its direction perpendicular to both vectors. In other words, vector A cross B is perpendicular to the plane that contains vectors A and B, shown in figure 2.2. The magnitude of the vector is defined as this, where angle phi between the 2 vectors is measured from vector A, the first vector, to vector B, and is in between 0 and 180 degrees. So here we have that sort of drawn out down here. We have the A and B. You find the vector product. It is perpendicular to both planes. So as we can see, we have the A this way and the B this way, and that's one plane that goes to the left, plane goes to the right, and what's perpendicular? One that just goes straight up. So imagine a cube. You have one face that is, or I guess you have one side of the cube that goes this, or one side of that edge of the cube that goes this way, the other one is on the other side, and then how do you get that vector, or that vector product is perpendicular to that face over here, so it goes straight up. So let's write that down. It is denoted by a cross product. It's denoted by cross. For example, A and B, like that. We get the vector product. And it looks like this. So the vector product has its direction perpendicular to both vectors. So this is perpendicular to both vectors. So I'm just going to use this little upside down T to show that's perpendicular. Perpendicular to both vectors. In other words, vector A cross B is perpendicular to the plane that contains vector A and B. Perpendicular to both vectors slash plane that contains A and B. Plane that contains the vector A and B. By the way, is my volume okay? I have background music, but I can't hear it because I just have it embedded into Streamlabs. I hope that it's fine. And the angle between the two vectors is measured from vector A to vector B. Angle between the two is measured in between. So we have, let's write it like this. Oh, is my internet okay? No, my internet, please! Hello, internet? Do not drop out. Do not drop out, internet, please. I'll still write, but I just hope it's stable enough to hold. This phi angle is measured from to B, like that. And my internet's back, right? Nothing dropped out. It looks fine. Hopefully. Okay, I think my internet's back. So we have that. It looks like this. The vector product of two vectors is drawn in a three-dimensional space. The vector A cross B is a vector perpendicular to the plane that contains vectors A and B. So the plane that contains A and B is the one that's like flat over here. Small squares drawn in perspective mark right angles between A and C. Right, so you got the perpendicular angles right in between. I think it's good to draw this, except I'm not very good at drawing. But I'll try and draw in purple. And then vector, in terms of the figure B, the vector product B cross A is anti-parallel to the vector A cross B. So maybe let's write that first. A cross B is anti-parallel so anti-parallel just means it's going in the same direction at the same, it has the same angle, but it's going in different directions. The other way around. I meant, yeah. So same angle but different directions. 2B cross A. Yeah! Alright, let me draw the little square thing. So here we have A. I think if I illustrate it better. But please, just like look at the actual reference on the textbook, because this drawing's not gonna be great. So here we have that, and then we have like the plane that basically this is the plane that contains both A and B right here. And then we have C that just kind of shoots out up from it. And then we also have a right angle. So this is 90 degrees difference. So right angle means 90 degrees. Is working. Okay, thank you for confirming. I was a bit worried because my internet just went kaboom. Screw you, internet service provider. Why do you suck? Okay, on the line perpendicular to the plane that contains vectors A and B are two alternative directions, either up or down, shown in this figure. And the direction of the vector product may either be one of them. So, okay, so you can get either the C and up and down. Yeah. In the standard right-hand orientation, where the angle between the vectors is measured counterclockwise from the first vector, A cross B points upwards to see that. If we reverse the order of multiplication, the vector must point downwards. This means A and B are anti-parallel to each other, and that vector multiplication is not commutative or but anti-commutative. And the anti-commutative property means the vector product reverses the sign when the order of multiplication is reversed. Ah, okay, I see what they're trying to say. I don't like how they explained it with the right hand rule. I'm like, we haven't gone over that as much. I feel like this is just gonna complicate things. Oh, everyone's internet is dying today, I guess. I also failed algebra. This is painful for my eyes. There's actually no math involved at the moment. So don't worry. It's just a lot of letters, which does suck. We're just learning about properties. So if you would like to learn, it's not as scary as it seems, I promise. It is spooky month though. So maybe it is. I did start off spooky month with physics. Well, my internet's back, so... Oh, my boss is back. I need to go. Yes, yes, go! Don't get fired! Good luck. My boss scares me. So as we said, it is anti-parallel. I'm going to rewrite that property again and explain a little bit that you can't switch the two. Cross A. And it is not commutative. It is anti-commutative. So that means that the directions point in different, the vectors point in different directions when you flip the cross products. So let me write down anti-commutative. Hello! Hold on, let me write this down first. Hello! Connor, hello! And thank you for the hydrate. I actually need a hydrate. I'm a bit dehydrated. Yes, hi Blue. I'm so happy that my alerts are finally making noises. How are you doing? How's your week going? I'm doing as well as I can be doing right now. So, like, not bad, but it could be better, but I guess things could always be better or worse. Not the worst has happened. How's your week going? It's going pretty okay. Actually, tomorrow I'm, like, pretty exhausted, so I'm gonna take a day off. So that's great. I finally get a day off tomorrow after, like, working for like, 10 months straight now, I guess. I didn't take a day off since the beginning of the year in terms of work. I finally decided to take a day off. I was gonna take a day off probably in like August, but stuff happened and then I just didn't take a day off in August. But yeah, tomorrow is my first day off in 10 months? 10 months? Alright, so it's anti-commutative, which means that's why it has the negative. It is not... I needed to sneeze. Sorry. I kind of felt like I needed to sneeze, but I also kind of didn't need to sneeze. It's like that in-between feeling, and then I ended up sneezing, so... Bless you, thank you. Will you be playing any games? Tomorrow, I actually won't be playing any games. I'll be visiting, some family and doing some chores. I'm, like, really behind on chores. That's okay. It's tomorrow will be more like a reset day for me. Maybe I will, but I probably won't. I do have a lot of games set for Spooky Month that I'm super excited about, that I've talked about earlier. But I need to get Cult of the Lamb extension up and running so I can play that. I see family chores though, I don't know. I see what you mean. I don't know, sometimes I find cleaning like therapeutic. It's like instant gratification that I don't get in my regular life anymore. Like, I work hard to clean and I can finally like see my good work happen. For my life, I can work hard all I want, but I don't get that instant gratification. Okay, I need to sneeze. corkscrew right-hand rule. Okay, so they will go into the right-hand rule. How do I explain the right-hand rule? I haven't done it for a long time. Alright, we'll just see what they say and I see if I can explain that. Right-hand rule is a common mnemonic used to determine the direction of the vector product. As shown in this image, the corkscrew is placed in a direction perpendicular to the plane that contains vectors A and B. I need to sneeze again. Okay, wow, I need to sneeze again. Why? Are my allergies kicking up? Hold on. Okay, your VTuber definitely sneezed. Yes, I always try to mute my sneezes because I'm worried I'll blow out people's ears. Okay, I think I'm finally done sneezing. Oh my lord, are you okay? I guess so. I think maybe my allergies are just, you know, just decided to start to act up in the evening. Okay, corkscrews placed in a direction perpendicular to the plane that contains vectors A and B, and its handle is turned in the direction its handles turned in the direction from the first and second vector in the product. The direction of the cross product is given by the progression of the corkscrew. I couldn't mute that one. Sorry. I hope I didn't blow out your ears. I need to blow my nose. Hold on. Alright, I'm fine. I'm fine. I think I'm fine. I just got like a sneeze attack. I don't know for what. You're in the trenches right now. My sinuses certainly are. This is me in a house of more than 2 cats. I love cats, but I'm super allergic to them. But I wish there were cats where I am. At least that would give me an explanation as to why I spontaneously decided to sneeze a bunch suddenly. A corkscrew. Okay, sorry, let me restart this part. The corkscrew right-hand rule is a common mnemonic used to determine the direction of the vector product. As shown in figure 2.3, a corkscrew is placed in a direction perpendicular to the plane that contains vectors A and B. So it's perpendicular, so it's either going up or straight down. And its handle is turned in the direction from the first to the second vector in the product. Oh, I see how they're explaining this. So my cross product is A and B, so I turn it from the A side to the B side. And if my cross product is from B to A, then I turn it from the B and A side. So that one goes above. Yeah, okay. The direction of the cross product is given by the progression of the corkscrew. Okay. Maybe you're allergic to vectors. Maybe I am. You know, it wouldn't be the first time I felt allergic to doing some work. Actually, like 2 days ago, I was like really struggling at work, and I just like had no motivation to do anything. And then my coworker was like, I think you might be allergic to hard work. Like, he said it as a joke, and I was like, yeah, I think I am. You just couldn't do it. And that's when I decided today, I'm not gonna work tomorrow. I'm gonna take a day off. I need to reset myself. So, I guess take a corkscrew and spin it from first vector to second. Spin. Screw. From first vector to second. Oh, and I guess a bit of an update on my karaoke stream that I'm gonna have. I'm probably gonna have that one in November. It will be themed. It'll be very interesting. But the songs I've chosen are actually really hard, and they'll be even harder for a very specific reason that I'll reveal once the time comes. But I'm really excited for that too. Lots of great things to look forward to. Okay, place a corkscrew, screw it from one way to the other way, and then B to A. And it always has to go counterclockwise? No, clockwise. No, but the spin depends. Wait, what do you know when to place it on top or the bottom? I guess if it's B to A, it has to go to the right. And this one also spins to the right. Okay, so the corkscrew always goes to the right, but where you put it depends on the direction. Okay, so the corkscrew always spins. Am I doing this right? To the right. So this is to the right, and what else is to the right? Let me think. To the right, and to the right. Yes, yes, yes! The screw always spins to the right. It's just where you place the screw depends on the vector order. This hurts my brain. I was an English major. English hurts my brain. Language hurts my brain. Alright, so the screw always spins to the right. Oops. And I hit the microphone. Screw spins to the right. To the right. Where to place depends on the vector order. All right, there you go. And we have a example that is really long with a long explanation. Examples, I will make that purple. Example 2.18, the torque of a force. The mechanical advantage that a familiar tool called a wrench provides depends on magnitude F of the applied force, on its direction with respect to the wrench handle, and on how far from the nut this force is applied. The distance r from the nut to the point where the force vector F is attached is represented by the radial vector r. Okay, so basically the distance between the nut and where your hand is pushing. They spent so long explaining that just for it to be the distance from the nut to the to the force where your hand is essentially pushing. This is why Blue and I are best friends. We both struggled. They're terrible math. We bounce each other out. Yes, I need the English majors to help me write things because I can't. I can't write things. I can't explain things too well and I can't write things too well. But like, can I do math okay? Decently? Yeah. Will I struggle with it? Yes, but I can still do it eventually. The physical vector quantity that makes the nut turn is called torque, denoted by, what Greek letter is this called? Is it tau? I'm just gonna call it T. I think there's a name for this Greek letter and I don't remember. And it is the vector product of the distance between the pivot to the force with the force torque is equal to the, what is that called? To essentially the distance and direction of where your nut is to the wrench and the force vector. So how much force you're applying and which direction your force is applying. Yeah. Okay, we'll write that down. So in this case, I'm just gonna put F, the vector, as a push force, which has a amount and a direction, and the amount is how much push you're pushing down, and then directions, of course, which direction you're pushing. So push, and it's got the amount and direction. Direction. Did I spell that right? I don't know if I did. And then we have the radial vector, which is the distance from the nut to your hand, I guess. And how far, as well as where, which angle? Or the direction of that too. How far and angle. Yeah. Yeah, I think that's right. How far an angle of your hand. Of a hand, I guess, is not your hand in this specific thing. Writing is too hard. Too many rules and expectations. Exactly. Exactly. I've actually failed writing. So you may have failed algebra, but I failed writing. Don't worry. We're in the same boat, just different. It's just repackaged. This is why people are good at certain stuff and other people are good at other stuff. To loosen a rusty nut, a 20 Newton force is applied to the wrench at an angle of 40 at a distance of 20 meters from the nut, as shown in the first picture. So, shown here. Find the magnitude and direction of torque applied to the nut. What would the magnitude and direction of the torque be if the force were applied at a 45-degree angle, as shown in this one? For what value of angle phi does torque have the largest magnitude? So they're asking for basically three things. In this example, they're asking for the torque applied of it when it is 20 Newton forces. The angle is 40. A distance of 0.25 meters from the nut. Part A2, I guess is what they're saying, is to calculate it when it is at 45 degrees. Oops. 45 degrees. And then part B is what angle has the most magnitude. So, I'm just gonna call it what should I name the magnitude? Most magnitude? I'm just gonna write most magnitude and then have the phi as a question mark. So most mag, and then we'll have phi as the unknown. So let's see what they say. We have this picture here. We adopt the frame of reference shown in this picture where vectors r and f lie on the xy plane and the origin is at the position of the nut. The radial direction along vector r is the reference direction for measuring the angle phi because r is the first vector in the vector product. Vector torque must lie along the z-axis because this is the axis that is perpendicular to it. Yes. So just like the previous example, we have that resulting cross product as the one that is perpendicular to both y and f. The z-axis that's perpendicular to it, we have r cross x, so we have it go into basically into the computer is where that force is coming from, right? Because we go from r to f and then r to f, or is it this way? No. Oops. It's this way. So it is going... No, yeah, it's going into the computer. This one, however, is not. It is going from this way. So... Wait, no. Wait, no, okay. So B is going into the computer, and F and the first one is going out of the page. Out of the computer, I guess. Because it screws this way. I don't know if I'm doing that right, actually. So it always turns right. This way. I'm thinking. Hold on, let me think about this for a moment. Yeah, no. Okay, so this one screws to that way, so in order for it to go this way, it needs to go out of the page. Okay, yes. So A is going out of the page, and B is going into the page, so into the computer, or out of the computer. I think. To compute magnitude torque, we use the equation to find the direction of T, which we use a corkscrew. I can't read. To find the direction of torque, we use the corkscrew right-hand rule. Yeah. So we have our equation here. Are they both going into the page? I don't know. I thought I understood that rule, but maybe not. I think that's something I'll have to think about after the stream to like really understand it, but this is all I got for now. So we have our torque, then we have our R cross F. Then we get our equation at the top, which is RF sine phi is equal to, and then we plug the stuff in. Basically, we have the magnitude of R, which was the 0.25 meters. Then we have our Newton force, because that is F, that is the scalar value of F. Then we have our sine, which is 45, or 40 in this case. 40, 40, 40, 40. It starts with 40, then we do 45. Yeah, okay. We have 40 degrees. Plug that into your calculator, which I do not have with me right now. And we have 3.21 newtons. I'm just gonna trust that they did it correctly. Sometimes textbooks actually do it wrong, so that's a bit funny sometimes. In this situation B, where the corkscrew gives a direction in the negative direction of the z-axis, physically that means the vector points into the page. Okay, so this is out of the page. Yeah, okay. So I was thinking about this right. We have the R going this way. That means the corkscrew is on the other side because you turn it to the right. That means the corkscrew is going that. So it goes out of the page, okay. And then this one goes into the page because we have the R here that we can just move over. And then we have that going from R to F, and it goes into the page. Okay. The magnitude of the torque is that. We have part B. So I guess that's part A, point 2 is really the one with the sine 45. Basically, we do the same thing we did for A. So we have the magnitude value of R, which is from that, the 2 magnitude, and then you put sine 45 degrees, which equals that. Now we want to have the most amount of magnitude possible, so that would mean that sine should equal 1. Right? The most amount of magnitude, sine with sine equals 1. Torque has the largest value when sine, when sine theta equals 1, which happens when phi is 90 degrees, because sine 90 degrees is 1. Physically, it means the wrench is most effective, giving us the best mechanical advantage when we apply the force perpendicular to the wrench handle. For the situation in this example, the best torque value is given as this. So when sine equals 1, we just have the full value of 0.25 times 20. And I hope my head is not blocking it yet. Nope, not just yet. I'll have to move the whiteboard up. Sine of 90, because sine of 90 equals 1. And that way you don't have to multiply this by any what is that called? Decimal place. And that's why it will be bigger. Any decimal place is less than 1, I guess, is what is more accurate to say. Any decimal place is less than 1. So you want to find the most amount of magnitude, you get the two scalar products, you multiply them, and then hopefully that your angle is equal to 1. That way you can get the full amount of magnitude from your scalar products, or your scalar. Significance. When solving mechanics problems, we often do not need to use a corkscrew rule at all. As we see now in the following solution, notice that we have identified that R cross F lies along the z-axis. We can write this vector in terms of the unit vector k of the z-axis. In this equation, the number that multiplies k is the scalar z component of the vector R cross F. In the computation of this component, care must be taken that the angle phi is measured counterclockwise from R to the second vector of F. So it's counterclockwise. So it's always turning to counterclockwise. I think that's better to say than turns right counterclockwise. Because that makes more sense to me. I mean, right is the correct way. I mean, turning something right is counterclockwise. But counterclockwise, for at least me, conceptually, just makes more sense. It's more clear, I guess. There we are. Coming in to say hi because I can't stay for too long. Hello, 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 strawberries. Yes, yes, yes. Thank you for saying hi. I appreciate it. Yeah, there we go. Counterclockwise, following this principle, for the angles we obtain are f sine of 40, which is that, for the solution, and we obtain RF sine negative 45 for the solution in B. Negative. But they didn't put it as negative. Maybe that's a typo? I'm not certain with that one. Well, I don't understand it. It'll be fine. In the latter case, the angle is negative because the graph indicates the angle is measured clockwise, but the same result is obtained when the angle is measured counterclockwise because of that. And 360 minus 45 is the same. And plus 315 is equal to negative 45. In this way, we obtain the solution without reference to the corkscrew rule. For the situation A, RF R cross F is that. For the situation B, the solution is negative. Another way for me to just understand this is which direction this turns to. If this turns left, that means to me that it indicates that the angle is negative. If this turns right, then that indicates that it's positive. So this looks like negative 45, well this looks like positive 45. I mean, I know that this is 40, but it kind of looks like 45 just from the drawing. I guess you can just always look back at your unit circle. From what I'm understanding from this, it depends on which direction it goes, and that's how you can tell whether or not it's positive or negative. And of course, because the unit circle is the same throughout, whether depending on which direction you go to, it is sine 315 is equal to sine negative 45. Yeah, that makes sense, right? Similar to the dot product. Let's move on though. Similar to the dot product, the cross product has the following distributive property. The distributive property is applied frequently when vectors are expressed in their component forms in terms of unit vectors of Cartesian axes. When we apply the definition of the cross product to unit vectors I, j, k that define the positive x and y and z directions in space, we find that it equals this, and they all equal 0 when you cross them with themselves. So let's write that down. We have the distributive property as well as the fact that they equal 0 when you cross them with themselves. Oops, that should be a plus. So similar to the dot product where this was just a dot, but it is now an X or a cross, you can distribute them. A cross C. Yeah, distributive property. Apply the cross product to the unit vectors, so cross product of unit vectors. You have I hat cross itself, I hat, and that equals 0, which means it also equals j hat cross itself. And when you have a x, y, and z playing, you also get the k. So you have cross product of all of that should equal 0. All other cross products of these three units must be vectors of unit magnitudes because I, j, k are orthogonal. As we remember, I, j, k are the unit vectors of the x, y, and z, which means they are perpendicular to each other. They make that right angle, the 90 degrees. For example, for the pair I and j, the magnitude is that, so it equals 1. The direction of the vector product I, x, j must be orthogonal to the xy plane, which means it must be along the z-axis. Right, the only vectors along the z-axis are k, negative k, and plus k. By the corkscrew rule, the direction of vector I, x, j must be parallel to the positive z-axis. Therefore, the result in multiplication is identical to plus k. I got brain pudding! We can repeat similar reasoning for the remaining pairs of unit vectors. The results of these multiplications are that. Okay, so, because they are orthogonal, so unit vectors are orthogonal. Or orthogonal. You have that 90-degree angle, so it's plus 90, or let's add the plus in front, or negative 90. Which means if you have I cross j, you get I, j, and then sine of 90, which is 1. You have 1 multiplied by 1 multiplied by 1, which equals, of course, 1. And then when you do I cross j, depending on the direction, you either get negative k or plus k because that is the unit vector of the z-axis. And they give us these lovely examples of it. Those. And this can sort of like illustrate which direction things should go. When it comes to the right-hand rule and where the vectors are. Yeah, I think that's right. I hope so. I hope what I said is correct. You know, I'm a failed engineer for a reason, so take everything I say with a grain of salt. How much more do we have? We actually don't have that much more left. And a lot of this is an image. Notice that in equation right above, 3 unit vectors I, j, k appear in a cyclic order? I don't know how to say that word. Shown in the diagram in the figure above. Very above. Oh, below! Sorry, below! Why is it 2.32? Oh, this is equation! Never mind, this is figure 2.32. I was like, why is the figure below if it has like a lower number? Slick, I think is how you say. Slick, okay. In the slick order shown in diagram below, not above, the slick order means that in the product formula, I follows k and becomes j, or k follows j and becomes I, or I follows j. J follows I before and comes before K. As in no L and am I reading this sick? Slick. Cyclic? Why don't we just Google it? I'm sorry, I can't read. I really can't read. I've got problems. Let me Google it. Silic? Oh, cyclic. Oh, hold on.
Cyclic.
I don't know if you can hear that.
Cyclic.
Cyclic. I can't read. Very low. Hello. Cyclic. Yeah. The cross product of two different unit vectors is always a third unit vector. When two unit vectors in the cross product appear in the cyclic order, the result of such a multiplication in the remaining unit vector is illustrated. So we have this, and it kind of goes in a circle, and then we can have that. So basically, the order is IJK. If you want to have I, then you go to J, K, and then you go back to I. I see. Okay, I'm gonna write a notes down for that after I finish reading this paragraph, but I think I get what they're saying. When the unit vectors in the cross product appear in a different order, the results in a unit vector that is anti-parallel to the remaining unit vector. The results with a minus sign shown by the examples in practice. When the task is to find the cross product of vectors that are given in vector component form, this rule for the cross multiplication of unit vectors is very useful. So what they're saying that I get from this is there's an order as to where this like Cartesian axis, or where the unit vectors representing a Cartesian axis, aka the IJK that represents the X, Y, and Z. The X, Y, and Z, the IJK that represents that, has a sort of pattern that you can use to find which equals what. So in this case, the plain case where you have IJK as like the cube, got K. The way that you can sort of figure out which is what is using this circle. So if you want to find out what I equals, you take I is equal to J cross K, and then that equals I. So you find what I is, go to J cross K equals I. If you want to know what J is, you go to J, and you get K cross I equals J. Yeah. So you sort of just go around the circle, and it always goes in this direction, unless in part B, or I guess in figure C of this. And thank you for the brain pudding! I definitely feel like I have brain pudding right now. It goes around as well. So if it's backwards, then you will have the I, J, this, whoops, and it's in the wrong color. We can't have that. It must be color coordinated. We have I, J, and then we got our K. And this one, K is negative. We got I, J, and then we go around the circle again. I think. So if you want I in this direction, we have negative K cross J, and that equals I. And then we want negative K, then we have J cross I. Yeah. So basically this sort of rotation of the axes explains what you should cross to get which direction. So let me write an example. So we go I hat is equal to J cross K. So you have I, go to the next one, J cross K is equal to I. Then we have, in this case, we can have I hat is equal to negative K hat cross J which makes sense because remember, when you flip the directions, when you flip the cross products, they are anti-parallel. So this aligns with our property that we learned earlier. Or sorry, it's anti-parallel and non-commutative. Commutative. I can't speak. Anti-commutative. So that means A cross B is equal to negative B cross A. And that equals like here. So once we switch the J and K, we get the negative K in the front. Yeah. So you can just use this sort of circle method to get what your unit vector is. Or the cross product of your unit vector. Suppose we want to find the cross product, A cross B for vectors, A that has that, and B that has that. So we got bxi plus by and so forth. We can use the distributive property, so the one we just wrote down here, where you can distribute the cross product to it all, basically. Distributive property, the anti-commutative property, I can speak, and the results in equation 2.38 and the results in this one. What is this one? Oh, where it crosses itself and it equals 0. Okay, so we can use all of these properties, the distributive, the anti-commutative, the one where it crosses itself and it equals 0, as well as the ones for the unit vectors where it essentially equals each other depending on where it is. To perform the following algebra. Oh boy, this is a big example. It's really long. I don't think I'm going to write it out completely. However, it's already written out for us. If I zoom in a little bit, is that too much? We can like really get our eyes on what this says here. So we have A cross B, we have it written out, and we can distribute the AXI to the B, same thing with the Y, and the AZK. So we have just a bunch of cross products. So we have the AXB, BXI for the first one, so that's our first sort of thing, and you continue doing that for all, I guess, all the scalar values of B, you could say. For all, like, it's kind of like variables, like when you have a polynomial and you just, multiply a constant in front of it. Yeah. Okay, and then you do the same where you have the Y, so you get J cross I, and J cross J, and J cross K, because we have that BZ. Same thing, we do that with the AZ all the way across. So the ones that are the same, so aka K cross K, J cross J, and I cross I, that's all zeros. Then we have this, and we can use this rule. We can use these equations and this sort of circular vector cross product rule where you kind of go around the circle to see what is what. So we have I cross J equals K, so we get K, that's a positive K. Then we have I cross K, so for that one we have I cross K equals negative J, because you're going the other way around. So maybe I should color this different color. I would make it red, and then I'll note that like the red is negative. This way. So red for negative. Negative, and then green is for positive. I guess I could have just put a plus sign. Yeah. There we are. Switch back to my iconic blue. You're nailing this word. What is it? Oh no. Wait, cyclic. Cyclic. Yeah, so it goes around. You basically do it for all of the cross products. So if you have J cross I, which would be negative K because it goes to the left, and then keep going, and then you'll get this. While performing algebraic, ugh, my nose. Why is my nose still so stuffy? When performing algebraic operations involving the cross product, be very careful about keeping the correct order of multiplication because the cross product is anti-commutative. I like this circle. I guess just look at the circle and look at the colors. The last two steps that we still have to do or compete our tasks are first, grouping the terms that contain a common unit vector, and second, factoring in. This way we obtain the following very useful expression for the computation of the cross product. Yeah, okay, so this is their resulting answer. In this expression, the scalar components of the cross product vector are this. We find the cross product in practice. We can either use this full equation, depending on which one seems to be less complicated computationally, or this one that has been broken up into the scalar components of the vector, depending on, okay, yeah. They both lead to the same final result. One way to make sure the final result is correct is to use them both. Guess and check. I mean, not guess and check. I guess do it twice and check. So let's write that down for the equation. EX and then I'm gonna write it down here. I ran out of room, so it's just plus. Oh my, this is so much writing. I've still never, like, I will never be used to this sort of, pad. This, what do you call this? Like a digital writing pad? I mean, like a mouse pad? Not a mouse pad. This is not a mouse pad. A digital writing pad to write things. I feel like my handwriting just could look so much better, but it's so ugly because I'm not used to it. I don't know how like digital artists do this. I have so much respect for them. Or even just like anyone who uses this on the daily. Like, it's so ugly. My handwriting. We have an example, and I guess this will be our last example for this chapter. But yeah. Example, we have that in purple because I want to make it purple. Purple and blue. Your handwriting. Oh, good evening. Hello. I didn't see your message. Sorry. Good evening. Hello. And also thank you for the follow, Slime. Hello and welcome to the strawberries. I hope you enjoy your time here. This is my example, my last example of this chapter of this stream, I guess, even. Wow, this was a lot shorter than I expected. Your handwriting is so much better than mine. You know, okay, I guess this is a very interesting thing to ask, but I've been told that I have very engineer handwriting. I don't know what that means, but I've been told that, and do you agree with that? I don't know what engineer handwriting means. but I've been told your handwriting looks like an engineer. People say like certain people have doctor handwriting, aka it's just incredibly messy and no one can read it. But I'm assuming that's what they mean by engineer handwriting, although I don't think anything particularly stands out from my handwriting that makes it specifically engineer. Anyways, when moving in a magnetic field, some particles may experience a magnetic force. Without going into details, a detailed study of the magnetic phenomena comes in later chapters. Let's acknowledge that the magnetic field B is a vector, the magnetic force F is a vector, and the velocity U of a particle is a vector. So we got 3 vectors. We got the magnetic field, the force, and the movement, I guess the velocity of a vector. The magnetic force vector is proportional to the vector product of the velocity vector with the magnetic field vector, which we express as this. The constant, I forgot how to pronounce this Greek letter. Is it psi? I feel like it starts with a C or an S. Anyways, this Greek letter takes care of the consistency in physical units. So we can omit physical units on the vectors U and B. In this case, let's assume the constant is positive. The particle moving in space with velocity vector U is equal to that, enters a region in a magnetic field, and experiences a magnetic force. Find the force on this product at the entry point to the region where the magnetic field vector is this. Part B is when it equals that. In each case, find the magnitude of the force, the magnetic force, and angle of the force to. I can't read. Find the magnitude F of the magnetic force and the angle theta, the force vector F, which makes the given magnetic field vector B. Oh my gosh, I feel like I just had a stroke reading that. Alright, let's write down the most important parts. Yes, I see engineer handwriting. But like, what makes a handwriting engineer? Like, I understand the doctor ones, because they write prescription at like the speed of light. So like, I get why it's messy. But what makes a handwriting specifically engineer? So this is a magnetic field. I spelled that wrong. The magnetic force, so we have F. Mag force. And of course, we have velocity of the particle. Okay, and then we also have the force vector, which is expressed as this. That is the Greek letter. Please do not comment on how it looks. I know it looks really bad. And we have the values of the velocity, so -5, we got the I hat, -2, got the J hat, plus 3.5. Oops. Okay. Yeah. I don't know, like, force trying to make it readable while also going fast. I see. I feel like this is not that readable. I mean, it's readable enough. I see what you mean. Like, I try to write fast, but it's readable enough. And then we have A, which is B. At 7 point. You know, one thing I noticed about my handwriting, the way I write Z's has differed from before I went to college until after I went to college. I used to write Z's normally, like that, but then after I went to engineering school, I started writing all my Z's like that. Even in my like regular, just writing something. If I write like a Z, I'll write it like that. Just out of instinct instead of writing it like this, because this looks like a 2. So to stop me from confusing myself, I started writing my Z's with like the center line in the middle. And now I write my Z's like that forever, and it looks silly. Because most everyone else just writes their Z's like that, but, you know, I write it like that. Find the magnitude of f. So basically, find f. Find f. First, we want to find the vector product of the velocity cross the magnetic field, because then we can determine the magnetic force using this. Magnetic force of the magnitude can be using the components. So this was from like 4 lessons ago, where we take the square root of it squared, and you can get the magnitude, and it's based off like geometry, basically kind of finding like the Pythagorean theorem, right? Yeah, it's Pythagorean theorem. It's not the quadratic formula. I haven't done any of this in so long. Or by computing the magnitude, u cross b, directly using the equation that. In the latter approach, we have to find the angle between the vectors u cross b. When we find f, the general method for finding the direction angle involves computing the scalar product of bf and substituting in the equation with, I'm assuming with sine or cosine. Yes, okay. To compute the vector product, we either use equation that or compute the product directly, whichever way is simpler. So okay, personally, in this case, I think I find solution 1 to be simpler for me. Because I like how it breaks it up. You could just do it all at once, which is what they're doing in part B. Oh my gosh, that's so loud. Hello, and thank you for the sub. That scared me. That's for sure an engineering Z. So it doesn't look like a 2 exactly. Okay, sorry. I'm gonna be a little sidetracked for just 1 second. I hate when textbooks and engineers do this. Like, who decided to have V and U as like as different variables? Like, I understand why people write Z like this for the 2. Like, can you have something like that for V and U? Because when I write them out, like, they look the same. One of them is just slightly more curved, but then when you look at it really quickly when you're doing your calculations and whatnot, it looks the same. And that's really something I hate, because it's always V and U. Like, you couldn't have picked a different letter. You couldn't have picked like T or something. Like, you couldn't have picked P. P would have been fine. P and U, or P and V. Or like I don't know. X, no, not X. X is used too commonly. Or like M. Why not M? Why not M and V or M and U? But it's always like V and U, and it looks the same. It's so annoying. Okay, sorry, rant over. Oh, by the way, for the person who just welcome to the Strawberries, I hope you enjoy your time here in our community. I didn't get to finish saying that. I just remembered the whole, like, oh, I hated that. I hated the U and V thing, and it annoys me so much. It makes my blood boil. I've legit gotten things wrong in exams because I rush and don't know which is exactly. I've done that too. Okay, I'll stop ranting about that. So they do it both ways. I think, sure, let's just follow the textbook and walk through how they did it both ways. So they decided to use this way for the first part with the multiple ones of it. Basically, you take the these values, like this one and this one and this one, as well as this one, and that one. You take those values, go back. I can't go back. I can't control Z, hello. I guess I'll just erase it. There we go. So basically you take those values and plug it in to this equation where we did the A cross B, and then you can get the resulting cross product. So they broke it up. I like how it looks when it's broken up. I think it's just easier for me to see it all. It does have the constant. Is it even worth putting? Sure, let's do that. So we have uy, which would be -2, times that, because it's by, so that's a 2, 4, and subtract 3, 3, 5, because we have 3, 5 as that. Then we have by, which comes from this, so that's a -1, and then you multiply it, and I'm gonna follow what the textbook says because I don't have a calculator with me. I never have a calculator with me anymore, which is 8.3. And you simply just do that for all of them, since you already previously calculated what A cross B is when it has all the unit vector component. The unit vector components. Yes. So when you have A cross my brain. When you have A as this, which is your unit vector components, and B as that, when you cross them, we have found out that you get this equation highlighted, or you can break them up into scalar components and have these values, which is what we're doing for the first one. Basically, you plug in all the ones. You just know that this is ux, uy, and uz. Can you see that? You cannot see that. You have ux, uy, and uz, and then you got the same thing, so bx, by, and bz. And you simply just plug it in, you get a bunch of values, and then you can get the magnitude of the force, which you get from this equation that we found out about 2 or 3 lessons ago, or 4 lessons ago maybe even. It's been a while. But we have that is equal to this. And we plug it in, so we have those values that we get from the textbook. And I'm not going to write it all out because it'll take me forever to write it out. But we take the 8.3, the 13.2, the 19.4 that we got from previous. After plugging that all in, (8.3) squared plus 13.2 squared plus 19.4 squared. Take the square root of that. We have a constant that you can factor out, and then you get this magnitude of that force. 4.9. Wow, I can't write. There we are. To compute the angle, we just take the angle of the magnetic field, because the u is the velocity of the particle. So we do the same to get that angle. We get the scalar value of the magnetic field, and then we can get the angle by this. Basically by taking the scalar product, which is the dot product, and then plugging it into that equation that we got from actually last lesson. I do know that this is last lesson. From the dot product, you can take that angle from the dot product. It's just an equation of the dot product. I guess you just refer back to that. So we have our scalar value of f. And let's get our scalar value of b, which would be just 7.2 squared, because this is the bx, the by squared and the bz squared. So when I say like, so the previous lesson we learned about dot products where the equation was given as the dot product of one vector and another is equal to the scalar of both, and then we have the cosine. So we basically take this equation and then go backwards because we can get the dot product of f and b, which you can just plug it into this equation right here. Yeah. You just plug it in. And I guess it results in 0, but I'll still write it out. Ugh. 19. It's 4.42 point that. And I guess that all equals 0 when you put it into the equation. Then you want to get that theta value, so you want to have the cosine on one side is equal to the cross of this. I mean, not the cross, the dot product of this, not the cross. It is not the cross, which is 0 over 24.9 and 7.6. But because it's 0, we know that cosine 0 is equal to 90. So that just equals 0, and then we take, I guess, cosine. Is it like this? Is that how you write it? Which is equal to theta, which is equal to 90. Yeah! Oh, you typed something, I can't read it all. The more I sit here listening to this, the more I realize how much I dislike doing this, yet the challenge and satisfaction of doing it. I feel the same. I hate this. This to me just feels like ridiculous busy work. Like, it feels a bit silly to do all this busy work. I put busy works in quotes. You can't see my hands, but I put busy works in quotes, but I'm like, but it's kind of fun. It's kind of satisfying to see it like kind of work out, but like it's stimulating my brain enough where I'm like interested in it, but it does kind of suck. I heard the hand quotes, don't worry. I'm happy you heard the hand quotes. It feels like busy work, and it's kind of annoying, but it's kind of fun to do because it stimulates my brain in the proper way. But it's also it's challenging enough where it stimulates my brain where the point's like, ooh, I kind of like that. But also it's like, why am I doing this to myself? This is stupid. I definitely feel that. All right, for part B. Part B, they're doing it the other way, where they take this and multiply it. But for this one, because B is only Z, it's only the component Z, so you only have J left, right? Because B is only 4.5K. So, am I doing that right? Am I thinking about this correct? dy. Oh, no, we have this. BZ here and BZ here. So you have two components. My bad. Wherever there's BZ, that stays, but the other stuff does not. Right? Am I doing that right? I think so. Yeah, I think I'm doing that right. Think so. So we have the cross of that. yeah, we have the first one where we have the ux times bz. Then we have that one that multiplies that. But where's this one come from? I mean, makes sense that you're oh, no. 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 Why? I'm confused. Do you want to continue Overcooked story at some point? Yes, absolutely, I do. When I start collabs, I always tend to, like, especially when it's got a lot of levels, I would like to continue. It just takes me a while to find, like, the time. But I know you guys, you and Kippy are like, it's okay to ask you last minute. But yes, I absolutely do want to continue Overcooked. You're carrying me so hard, so I feel kind of bad. But I guess that's part of it. You'll have to carry me some more. That game, like, is very fun, though. I do very much enjoy it. Am I thinking about this correctly? I feel like I'm not doing this right. Oh, no, I'm not. I'm stupid. It's just a distributive property. Because I don't need to do all of this. I can just use the distributive property. I mean, this equals 0, so I'm not wrong. I missed what was right in front of me. So it is correct. I am correct. Okay. So you basically use these two. The reason why they do 3.5 times 4.5 is because the k crosses out. I mean, equals 0. And I can't believe there's no undo button. Does that work? I think I might have pressed a button on my pen. Oops. No, I might have pressed something on my pen and I didn't mean to. But there it is. That's what I was thinking about incorrectly, and I understand it now. So k cross k is that. Or you can use the distributive property because it's much easier, which is what they did. And that should be the way to do it, actually. Don't feel bad. I've played through the game like 6 times with all different people. Oh, okay. Hi, Yoshio. Hi, Blueberry. Hello. Blueberry's very accurate because it's spooky time. We're almost finished with this whole chapter, the spookiest of all, and we can finally move on to forces, I think, in the next chapter, which I'm excited to do next month. But I also have horror games to play that I'm scared of. I'm so excited when I continue. It was really a blast. I'll definitely find the time. Hopefully, in October I can stream a few more times than I did this September, the past September. Yeah, position displacement and average velocity. Yeah, finally, real physics. More fun stuff. But okay, let me finish this last example. And then I can have like a small little chatting session after. Let me finish this chapter. Alright, so we use a distributed property. For this, the way that they showed it in this, you could use the other methods as they showed before, where you can just plug it in here, or you can plug it even in here. And that would all work. It would all equal the same, but the distributive property is the easiest. No, I don't want to add a note. Alright. So, in this case, we have F, we find the force, the little constant in front of our velocity, cross B, which is our magnetic field. Our magnetic field only goes one direction, one way, and then we have that. Negative 50 times this, which is 4.5, I cross K, plus 0, 4.5, J cross K. And the K cross K cancels out, so I'm just gonna put a plus and dot 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 and then K cross K. And that equals, oops, that equals 0. So then we just end up with this part and that part. Which means it is equal to Yeah. Spooky time. I love spooky time. I saw you were playing Baldur's Gate. I couldn't really get into the stream because I was having technical issues. But I'm gonna start playing Baldur's Gate again now that the weather cooled down. So I'm excited for that. I'm still in Act 1, despite playing it for how long. I played it for so long, and I'm still in Act 1. But it's really fun. I definitely forgot a lot of the controls. So I'll need to relearn that, for sure. I saw you were playing with, your friends and like, Sky, and... that must be cool. You were playing it last time, too. I did check in with you the previous time you played Baldur's Gate. I think you're at, like, the temple? Where you kind of, after you just crash landed and you're at the small little temple with the one that has withers in it, I think. I need to watch more of other people's streams. I've been lacking so far recently. Usually, sometimes I would just like listen to it while I was working, but recently, I've been a bit scared to do that. Alright, so we have that magnitude again. We find that magnitude. The magnitude of the force. So we have 9 squared plus 22.5 squared. The other one's 0, so we don't care about that. And we have the little constant in front. And of course, we can once again find the angle where we take the F cross B. In this case, the same thing happens where they have 0, which means that the angle is once again 90 degrees. Is my head blocking it? Nope. 90 degrees. Just like the previous one, so it's the same as this that we had. Then that means that the magnitude force of F is perpendicular to the magnetic field vector B. The significance of this example is even without actually computing the scalar product, we can predict that the magnetic force vector must always be perpendicular to the magnetic field vector because of the way this vector is constructed. Namely, the magnetic force vector is the vector product F is equal to that constant times velocity across the vector of the magnetic field. By the definition of the vector product, vector F must be perpendicular to both vectors. So that means that it is 90 because it's perpendicular. So that works out. Anyways, that is the last example of this chapter, and we finish it off with this. In conclusion to this section, we want to stress that dot product and cross product are entirely different mathematical objects that have different meanings. The dot product is scalar, so we get a scalar value, so it has one piece of information. The cross product is a vector, so that gives you two pieces of information. Later chapters use the term dot product and scalar product interchangeably. Similarly, the cross product and vector product is also used interchangeably. So let's do that. For the check your understandings, I used to do them, but I felt like they always took so long, and then my voice started to go. So now I just do the regular ones. I mean, this textbook is free, by the way. If anyone here is like new and wants to actually like learn it, I tend to go at a snail's pace. I go at a snail's pace because it's the most comfortable for me. I'm not joking when I say I'm learning this with everyone because I have not touched this stuff in years. So yeah, it's free. There's also, I have many great things to say about this book. It's all open source. There's textbooks on multiple subjects, and I think it's great if you especially want to learn something else. Some of them are university level. Like technically this textbook is university level. There's like help on, if anyone knows what like AP exams are, I think the textbooks here can also help with that. I think it's great. So from the final takeaway of this whole vector cross product, dot product, and all of its glory, we find that the dot product is scalar, which we had mentioned on the previous stream. And hello, Water Pupper. I have not heard from you in a while. Thank you for stopping by. Been here for like an hour. My last brain cell died. I wish I was smart enough to understand this. To be fair, I barely understand this. Dot product is scalar, and cross product. Oh, my voice is starting to go. Is a vector. Yeah! And cross product. Oh, I wish I could erase. What happened to my undo button? It was working earlier. Cross product. Can also mean slash. Actually, I shouldn't put slash. It looks like I'm dividing it. Is a vector product. And hello, Ray. Is a vector product. And dot product is a scalar product. Yay! That's great. I need to drink some water or else my voice is gonna snap. Alright, shall we do a review of this last section? Let's scroll back up to where we were. And let's do a review. If you listen to enough, I think you can understand it soon. Sometimes I don't even understand what I'm saying, so nothing against you. Nothing against you. I definitely think there needs to be more supplemental information. Alright, here we are at the top. Okay, so today we learned about the vector product of two vectors, aka a cross product. It is shown with this cross, and the magnitude is defined as this. So we have that here, and we have that here. Perpendicular, the cross product is perpendicular to both vectors, and the cross product is perpendicular to the plane that contains both vectors. Right? That makes sense, right? So basically, we got our C vector, which is this one that goes up, our C vector, and it is perpendicular to the plane that contains both. So we got like imagine like you draw a square here, and then you have a vector that goes up because that's perpendicular. So we got that 90-degree angle on both. And it is not commutative, but it is anti-parallel. So if you switch the A and B around, it is anti-parallel, which means it goes into an opposite direction. So A cross B goes up, B cross A goes down. And the properties are anti-commutative, which means the vector that you switch out has a negative in front. It is not commutative. To figure out which way the vector goes, you can use the corkscrew right-hand rule. So for this, you imagine you have a screw, and then you go from your vector, from the first vector, which in this case is which in this case is A, to the second vector, which is B. Then you imagine trying to screw something in the direction of A and B, and it always has to go counterclockwise. The screw only turns counterclockwise. Wait, is that right? Is that right? No, that's not right. It works for this one, where A to B. Okay, well... okay, how do I think about this? Okay, no, yes, okay. So the screw always goes counterclockwise in the direction of the way you're turning it, if that makes sense. So because in this case you're going from upside down, you're turning it counterclockwise to me. And for the other one, it goes from B to A, which turns clockwise. I still don't understand the screw, like, analogy. But basically, I guess what they're trying to say, maybe I should erase this. Is that the direction of where you put the screws, which way the cross product goes. For me, I just do it mathematically with the negative sign. If it has a negative sign, it means it's going down. If it's positive, it goes up. So this one, you screw it up because the direction goes from A to B because you're doing a cross product from A to B. And then this one, the direction goes from B to A, which means you're screwing it this way. And therefore it screws down. Yeah, okay. So if you turn it right way, that means it's starting to go into whatever you're screwing into. So imagine like this upside down, you'd be screwing it into. I zoned out. Is this a right hand rule moment? It is a right hand rule moment. The thing is, I don't like how the book explained it. For me, I just look at my hand and I see arrows going through it. Like I can visualize arrows going through it, but because the book explained it as a corkscrew, you can see B to A as unscrewing as it goes down, if it makes sense. I see B to A as screwing into it. It's screwing for A, I guess image A, it's screwing into it upwards, and B is screwing into it downwards. And that's what it's trying to say. I guess it matters depending on which way you screw it into, right? Turn right. Okay, no. So the screw always tightens to the right. I thank you by the way for that. That's a good way to think about it. So screw tightens to the right. Tightens. I can't spell tightens. T-E-N-S, tightens to right. And then that means that if you are going from A to B, which the vector goes from left, that means it's going up. And then if it goes from B to A, which means it goes from right to left, that means it's screwing down. Okay, that makes sense to me, right? So the screw always tightens to the right. You go from the first vector to the second, which is A to B, which means you're going to the left, which means it is upside down. And then for the next one, you have B cross A, which means the screw is going from right to left, which means it's turning clockwise, which means tightening down. Yeah, okay, that makes sense to me. Very stool-like, I agree. It looks like a stool. That's true, it does. It looks like it sit on it. I wish they just had a normal screw. I think that would be more aesthetically pleasing. But yeah, basically, if you turn it right, it means it's going that direction, or whichever way it's going. You just look at which vector is first, trace that, go to the second vector. In this case, it's going to the left. If it's going to, like, it's turning left, which means that it's going up. In this case, you're going from B to A, which means it's turning to the right, and that means it's going down. Okay, that makes sense. And then next, we have an example with torque. We are given that the torque is equal to the cross product of the distance of the nut and R, as well as our force of where we are applying. So same thing, we have that right hand rule where we have this going into the page, right? Yes, because we can shift the R vector down to where this dotted line is for like visual sake. It helps us visually. Shift it down. It's turning to the right, which means it's screwing into the page. We have this one where we have R cross F. where it's screwing to the left, which means it has to screw out of the page in order to get which direction we're going. For this one, to just get the cross product, or the vector product, the magnitude of the vector product. To get the magnitude of the vector product, we simply just take that equation. They give us our angle of where the force is applied to, so that's 45. You do the math, you plug it in a calculator, and you get these two things. To find something that has the most amount of force, like the angle, we simply make sure that that angle is equal to 1. In this case, sine 90 is equal to 1, and then we can get the most amount of vector, the magnitude of vector, the vector magnitude. And you do that. And then, similar to the dot product, it is distributive. So it's got the distributive property. When we have the unit vectors, a unit vector cross itself is just 0, and a unit vector cross another one is equal to 1 or -1, depending on which direction you go. So we get these two equations where it's equal to 1, and you get that. And a good way to figure out whether or not it's negative or positive, depending on which way you go, is to use this sort of like circle diagram thing. So you have, if you want it to be positive, so I is equal to J cross K equals to I. But if you want it to be negative, so we have I is equal to negative K cross J is equal to I. So we can have like this rule like this. And then keep going, we have our vectors A cross B, and they gave us these equations after crossing them all and writing and basically distributing each vector unit. Each unit vector out into the other cross product, and for that you get this resulting vector, and from that we have our AY, BZ, AX, AZ, and so forth, as long as with the B, and then we can get our components of the scalar vector, and from that we can calculate the velocity of how something's moving based off the cross product and the magnetic field. To get the magnitude, we use this equation that is based off the Pythagorean theorem, except with 3 components. This time you can still get the magnitude that way. You simply just plug in the values into this equation and you can get it out. Yeah, you get that magnitude, you get this, and then if you want to get the angle, you can go back to the dot product and find that angle. Yeah. And similarly with the other one, you can use distributive property, and you can use either one of these methods. You can just plug it in, use the distributive property if it can cancel out. For example, the part B only has the magnetic field as only having 1 unit vector component, and with that you can do the distributive property. Main important things is the dot product is a scalar, the cross product is a vector. So we only have one value or one piece of information here. The vector gives you 2 pieces of information, and the names are interchangeable between cross product and vector product, as well as dot product and scalar product. Yay! That was a absolute train wreck of a what is that called? The absolute train wreck of an ending that help us understand. And on the YouTube side, please talk in English. Sorry, I don't want to be like that. Like, I want people from anywhere to be able to comment, but for what is that called? For moderation purposes, please speak in English. I'm gonna have to remove your messages, not because I don't want to respond, not because it's for moderation purposes. I have to have it in English. So, yeah. Please read my rules. I have it in the rules. Please read my rules. And if you violate this rule too many times, you will get banned. So please don't. You can use a translation tool if you'd like. That's totally fine. It just needs to be in English when you post it in the chat. But yeah, that was my lesson so far. I hope you guys enjoyed that. Oh, rules are way too hard to follow. That's my message in chat. I hope you enjoyed this stream. I don't really have anything else for today. But yeah, look out for next week. I'm really excited to start spooky season. I think I'm gonna start playing, what's that called? Night... something in the woods? Oh, Night in the Woods. I want to play Night in the Woods next stream. And, Love Ghosty. And then the stream after that, I want to play Baldur's Gate and Observation Duty. That will be a very stressful week. I will put a heart rate monitor when I play Observation Duty. If it gets too high, we'll have to pause. I don't want to get a heart attack. But yeah, hello, this is quite interesting. Hello! And I'm glad you find it interesting. Next time I do a physics stream, like I said, it will be on velocity and position and movement, which I think is more fun than vectors. I feel like position, displacement, and velocity. I think it's a bit more fun. I've always thought of traditional physical kinematics to be more displacement, velocity, and position. But yeah. Hopefully you guys like the stream. I will be raiding someone. I don't know who to raid yet. Let me find out. And if you'd like to join the raid, that'd be much appreciated. And if not, absolutely no worries. I'm an engineering student. It's nice to see the basics again. I'm a failed engineer, and I'm trying to relearn the basics. Too bad I came in late. The VOD's always there, and also I do these types of streams every month, so if you like to learn about the next section, feel free to. Of course, no pressure if this is not necessarily your thing. Let's see. Who should I raid? I'm trying to find another VTuber who's streaming science and technology right now. There's a person who is not a VTuber, but they are doing electronics repairs and builds. Should I rate them? Someone else? Maybe someone else. I don't know. I'm always like so nervous when I try to raid into someone who's not a VTuber. I feel like maybe they just won't understand. Okay. I'm gonna find someone on my following list. I'm just too scared to raid someone who isn't a VTuber, unless they raided me before. Then I don't feel that bad. Let's raid Jazzy. I haven't raided Jazzy in a long time. She is a 18+ streamer, so I guess be aware of that. I know that's not something that I put in all the time. They're electronics person. They seem far. You know, you'd be surprised. I have a friend of Kippy. Oh, wait, yeah. Tell me who's Kippy friend is. I'll raid them. Maybe I'll switch to my chatting background. Actually, since I don't have to work tomorrow, I can chat a bit longer. Oh, I've heard of them. I thought I've not followed them. I thought I did. Yeah, I think I definitely heard of this person before. Probably through you. You're sweet to anyone that isn't me. Well, we'll raid Venusaur. Here's the link if you'd like to join us in the raid. on the YouTube side. And if not, absolutely no worries. Please take care of yourself. And have a good time zone. Let me set this up really quick. I really need to change that message, but it's fine. We'll keep it as this. I kind of like the derpy robots for the raid message, at least. All right, let me switch to the screen, and then we'll be raiding in a few seconds. Hold on, the scuff is coming. Raid will happen in 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Beep boop. Bye everyone. Bye bye.